Hi guys, this is Dr. Bay here, and today we're going to learn about part one of the alkyne reactions. We're going to go over alkylation, birch reduction, catalytic hydrogenation, as well as ozonolysis. So stay tuned.
Organic chemistry,
Taught by Dr. Bay.
reaction mechanisms,
Reactants to products.
retrosynthesis,
Target deconstructing.
molecules, spectroscopy. Soaring through the sky, triumphantly fly, give rise to the complexity of life. Living on a dream across the seven seas, learning about spectroscopy. Organic chemistry.
Alkynes are molecules containing a carbon-carbon triple bond. Recall that a triple bond is made up of one sigma bond and two pi bonds. Alkynes are similar to alkenes in their ability to function as either a base or a nucleophile. Many alkynes are found in nature, like this molecule, which is found in the skin of poisonous dart frogs. As you can see, it contains two alkyne groups that create structural rigidity in this molecule. In general, alkynes are less reactive than alkenes, but various electrophiles can be added across a pi bond of an alkyne to form different products. There are two types of alkynes, a terminal alkyne, which is monosubstituted, and an internal alkyne, which is disubstituted. Terminal alkynes can be turned into a good nucleophile using a strong base. For example, NaNH2, NaH, or LDA can be used to deprotonate a hydrogen part of a terminal alkyne. In this example, NH2- deprotonates the hydrogen atom, and the bond forms a lone pair of electrons onto the alkyne carbon, which gives it a formal charge of -1. The conjugate base of an alkyne is called an alkynide ion. This makes it a strong nucleophile that could then be used for an SN2 reaction. For example, let's say we wanted to form the following product where we added an ethyl group to the end of this particular alkyne. First, we use a strong base to deprotonate the hydrogen of a terminal alkyne. Then we can use the alkynide ion to undergo an SN2 reaction with the following primary alkyl halide to produce the desired product. Now let's talk about how an alkene can turn into an alkyne through a double E2 mechanism. The first step is to undergo halogenation with an alkene in polar aprotic solvent. Then the second step is to perform E2 with the strong base twice to form an alkyne. In this example, the first arrow starts in the middle of the pi bond of the alkene and attacks one of the bromine atoms in Br2. The second arrow is from the first bromine atom and goes towards one of the carbons of the alkene. And the third arrow goes from the bromine-bromine bond to form a new lone pair of electrons on the second bromine atom. This forms a bromonium ion, which should look familiar to you. Then, in the next step, the second Br- comes in, attacks one of the bromonium ions, which then opens up to form a vicinal dihalide. Then a double elimination occurs using two equivalents of NH2-, where each base deprotonates a beta hydrogen, a pi bond forms, and the bromine leaving group leaves. Both E2 reactions occur simultaneously, which is why both sets of blue and red arrows are drawn together, and then from here you form the desired alkyne. In this next reaction, we can form a terminal alkyne starting with a geminal dihalide with excess NaNH2 and NH3 followed by water. Just as a reminder, a geminal dihalide is when two halogens are bonded to the same carbon atom. The first step is that a double E2 mechanism with the geminal dihalide occurs using two equivalents of NaNH2 dissolved in liquid ammonia. This forms a terminal alkyne. Then another mole of NaNH2 is used to deprotonate the terminal alkyne to form an alkynide ion. Then, after the alkynide ion is formed, Water is used as a proton source to protonate the alkynide ion, which then forms the final terminal alkyne. So in total, 3 equivalents of NaNH2 are required, where 2 equivalents are used for the two E2 reactions, and 1 equivalent of NaNH2 is used to deprotonate the terminal alkyne and form the alkynide ion. Now let's talk about ozonolysis of alkynes. There are 2 types of ozonolysis reactions that could occur, but you do not need to know the mechanisms for either reactions, just how to predict the products of each one. The first reaction is if ozonolysis is performed with an internal alkyne followed by the addition of water. This forms 2 carboxylic acid molecules. And the second ozonolysis reaction is with a terminal alkyne, and this produces 1 carboxylic acid and 1 carbon dioxide molecule. The last set of reactions that you'll learn about in this video fall under the category of alkyne reduction. If you use H2 gas and a metal catalyst like palladium, platinum, or nickel with an alkyne, you'll reduce the alkyne to all single bonded alkanes. If you use H2 gas with Lindlar's catalyst, then you'll form a cis-alkene where the 2 hydrogen atoms add via syn addition across the pi bond of the alkyne. And lastly, if you use sodium metal and ammonia with an alkyne, you will form a transalkene. You do not need to know the mechanisms for the 2 catalytic hydrogenation reactions, but we will discuss the birch reduction mechanism in class.
Organic.